Last up will be Terry Keating, who's a senior scientist from the US EPA, Office of Air and Radiation. At EPA, he advises senior management on a variety of issues, from the implementation of ozone and fine particle standards to intercontinental transport of air pollutants and the linkages between air quality and climate change. He's done research at the Kennedy School at Harvard and was also a fellow at the American Association for Advancements of Science fellowship program, which advises legislatures, agency decision makers and stuff using sort of a science kind of role. He's an expert in urban and regional air pollution as well as stakeholder participation. He has a master's degree in public health and a PhD in environmental sciences and engineering from UNC at Chapel Hill.
So I'm Terry Keating, and I'm from US EPA's Office of Air and Radiation. And I'd like to start off by thanking Tracy Holloway and the Wisconsin Energy Institute for having me here and getting me here, and to my fellow panelists and to the panel that spoke this morning for really setting this up. I'll try and move through some things quickly here. The main messages that I want to convey are, number one, satellite imagery has really changed our understanding of air pollution as a global issue. Air pollution sources globally are expected to continue to grow, and their influence domestically will grow unless new policies are implemented. So there's important room there for policies. The observations from satellites and along with satellites come sort of global models, data information systems, and things like that. These are becoming very important tools for us on the domestic front to understand and account for global influences on US air quality, and on the international front to motivate and enable emission reductions of sources of air pollution in other countries. And I'll return to those sort of key phrases. And finally, my sort of message is that it is in the US national interest to pay attention to what's happening on the global scale and to promote public awareness, technical capacity, access to information around the world about air pollution. And then to encourage the integration of air quality objectives into sustainable development goals, again, around the world. So a picture is worth 1,000 words, they say. Is this going to go? Maybe I have to go there. Yeah. Okay. So there's lots of different animations of satellite data. This particular one is a rather old one. It's the first release of CO data from the MOPIT instrument from the Terra satellite back in 2000. And I think it's imagery like this that help not only scientists, but has helped decision makers start to think about and understand air pollution as a global phenomenon. That when you can actually see observations where you can watch air pollution episodes develop, evolve, be transported, and impact across the globe is very, very powerful. And so this is one of the reasons why I like this one, is because it is CO, which it's funny when you talk to an air pollution control audience, because we tend to think of CO as a very local issue, right? We think of street corners and street canyons and things like that. And here you've got CO episodes being developed. You can watch episodes, sort of plumes develop off the east coast of the United States and be carried across the Atlantic, et cetera. And you can see fires burning in different parts of the world. Okay. So one is just the imagery. Another really more recent application of satellite information that has really sort of changed the dynamic is the application of satellite data in the global burden of disease study. And so the global burden of disease study is an effort to understand the relative contribution of various disease risk factors. And the first time that the GBD study was done They estimated air pollution effects based on data that they could manage to collect from cities around the world. And so they had some pretty good data for North America, they had some pretty good data for Europe, but the rest of the world was pretty sparse and pretty poor quality. As a result, air pollution was not ranked very highly. When they tried to redo this for 2010, the team led by Mike Brower from Canada went to Randall Martin and said, hey, can satellites help us here? And Randall said, sure, we can use satellite observations and global air quality models to create global coverage of PM exposure, fine particle exposure, across the world. And that's exactly what they did. And as a result of that, air pollution, here I've highlighted household air pollution is the top one with the red arrow. The second arrow down is ambient fine particles. So air pollution sort of moved very quickly up the table of risk factors. Together, household air pollution and ambient air pollution contribute about 7 million deaths annually worldwide. As a result of this, international organizations started to say, whoa, we need to do some more work on air pollution. And so in June of last year, of 2014, the governing body of the UNEP program, the United Nations Environment Program, passed a resolution asking for countries and for UNEP to do more to address air pollution. The World Health Organization, their governing body passed a similar resolution in May of this year. Both of them are developing plans right now to implement that and report those plans back to their respective assemblies in May of next year. Both the UN Environment Assembly and the World Health Assembly are both meeting in May in separate meetings of 2016. None of that would have happened without the look from satellites. And so I think these are really important applications which are changing the sort of view of the world. So what is going to happen? What's our outlook for global air pollution? Well, I co-chair a group under the LRTAP Convention, known as the Task Force on Hemispheric Transport of Air Pollution, along with Frank Dentner from the European Commission's Joint Research Center. And we're looking at a set of future projections that were developed by EASA, the International Institute for Applied Systems Analysis, with some funding from an EU project. And what they've done is they've looked at the International Energy Agency's projections, which were published in 2012, and developed really a series of scenarios based on two climate policy projections. One that relates to sort of 6 degrees global warming, and the other is a 2-degree global warming scenario. So in this plot, I'm comparing the two scenarios, which are the lines, to the two climate scenarios based on the IEA projections, to the family of projections from the what are called the RCP scenarios, which are the reference concentration pathways developed for use by the IPCC. So you can see that the IEA sort of captures or is in the same range for some of these, and others there's a little bit of difference. But in terms of CO2 emissions and the sort of overall implications, they sort of bound the range of the RCPs. Now, the RCPs that are used by IPCC are not very useful for looking at air pollution scenarios, because they're really developed to look at CO2 and global energy scenarios. And so for air pollutants like SOx, NOx, VOC, CO, they all use what's called a Kuznets curve, where they assume that as GDP increases, air pollution increases, and then at some point it peaks out, and as countries get richer, they start to implement air pollution controls. And so if you look at the RCPs and you look at the details for NOx and all of those, you get out to about 2030 and everything starts to turn down, and air pollution control just happens, right? And but if you're going to actually look at what does it mean to develop an air pollution control policy, you need to be more explicit about what the technology is that's behind that assumption. And so EASA developed sort of 3 air pollution control scenarios. One is their best guess at sort of current legislation. The second is a sort of pessimistic scenario where we don't add any further control beyond 2015. And so we keep basically the emission rates the same, and we allow activity to continue to increase. And then the most optimistic scenario where we turn everything in the control database on and throw every control measure you can think of, whether it's feasible to do that or not. It's just whatever technological control you can put on, we do that. So we have 3 scenarios, and this is what they end up sort of looking like on a global basis. Again, comparing the 3 lines are those 3 scenarios, and the gray range is the range of the RCP scenarios. And so you have SO2 on the left, NOx in the middle, and black carbon on the right-hand side. And so what you see from this is, first of all, their scenarios are a lot more pessimistic than the RCP scenarios that just assume that everything starts to get better after a certain point. And also you see that even with some current legislation, a lot of emissions continue to increase over time, and that there's a lot of room for improvement for air quality policies. That bottom line there's lots of technical options that can get us down much farther. So there's lots of room to improve. If we impose a more ambitious climate scenario, you get this red line as your current legislation with sort of extra climate controls. And you can see that for some pollutants this helps a lot. You can imagine for SO2 things are going down because you're doing more and more switching away from coal to natural gas and other things that lower sulfur. NOx, not so much, right? Doesn't change things as much as it stabilizes it, but it doesn't really create much benefit. And then there are some of the emissions which really aren't necessarily energy related. Some of the VOCs, ammonia, that are important emissions that really won't be affected that much by climate policies. And then you have methane here. And methane is really interesting, and one of the things that we found in our work under the Hemispheric Task Force in our first phase of work, very much thanks to Arlene Fiore's work, was that what's going to happen to ozone globally over the long term is very much a function of what happens to methane globally over the long term. And that the change in methane can actually offset changes in ozone, other ozone precursors at a regional scale over the long term. And by long term, I mean over sort of decadal time periods. So it's really important that we start to look at what these different, what the scenarios are, what the potential opportunities for control are, and start to incentivize and motivate those things moving forward. So the bottom line about the future air pollution emissions are that, one, if you start looking at the air pollution in more detail, you get a much wider range of possible outcomes than we've seen in, this is the RCPs, but that's not the right definition of what an RCP is. It's a reference concentration pathway. The scenarios, they highlight the importance of enforcement of existing policies. So we actually need to do the things that are on that current legislative scenario, or things will get worse. And in the long term, we need to do more, and there's lots of opportunity to do more. One of the things that we would like to know, though, is so where are those opportunities, and where might you do it, and where might it have an impact? I'm not going to go into the details of this, but one of the tools that we've used to look at this is we can use modeling tools to look at those scenarios. This is a particular tool, the FAST tool, which was developed by the Joint Research Center in Ispra, Italy, and by Rita Van Dingenen and my co-chair of the Hemispheric Task Force, Frank Dentner. And so we can use these tools to look at sort of what the implications of these scenarios are. So here I'm showing some results from FAST, looking at comparing the 2050 current legislative scenario to the 2050 maximum feasible reduction scenario. And so you can think of these as, in each of 4 different regions of the world, for improvement in that region, where does the benefit, where are the opportunities for controlling sources coming from? So where's the real opportunity? And so for fine particles, if you look in China, it's mostly from China. In India, it's mostly from India. Same thing in Western Europe, same thing in the US. Okay? But now if we look at ozone, story is still the same. For China, most of the opportunity comes from China. In India, most of the opportunity that's out there comes from India. But for the US, there's a lot more influence from the rest of the world. So the US here is, the US color is green. On the bottom, it becomes a much smaller fraction of the total opportunities that are available out there in the future. And for Western Europe is the light blue color on the bottom, not the light blue color on the top. And so the point of this is that the US and Western Europe really do need to be engaged and understanding and motivating and enabling air pollution control in other parts of the world, because that stuff is going to come back and have an impact. Okay, so what do we need to do about it? Well, this is where I come back to those key phrases of domestically, we need to understand and account for that influence. So when we're talking about managing air quality in the United States, we need to understand where the ozone, and here ozone's a good example. This is developed for ozone. Where's that ozone coming from? Because we have different mechanisms within the Clean Air Act that we can deal with these different pieces of the puzzle. But we have to be able to quantify each of those contributions. And that's a very difficult task. The tools that we traditionally have used in air quality management are, we have a ground-based monitoring network, we have regional air quality models, and those regional air quality models are fed by emission inventories. This is sort of the traditional tools. We have a sparse number of SONs that are launched every day, and we use that to get some idea of what's going on in the vertical. Okay? That's the way we have been doing things for most of the past. But if we're really going to address the challenges that we have now, and what you've seen examples of, is we need to start bringing in a whole lot of other sets of tools. We need to bring in satellites. Right now we have mostly polar orbiting satellites with geostationary potentially coming down the road. We need to use ground-based remote sensors. We haven't talked a lot about LiDARs here, but they're very powerful, informative tools. The idea of similar sorts of instruments that you can put into space, you can put on the ground and be looking up. Aircraft-based instruments, and feeding that information into global models which are informing regional air quality models. The people that you've seen present in this morning's talks and in today's are doing this. The issue is, this isn't the way we've done things in the past. This is new. And all of this needs to be integrated in new ways, where we're thinking about data integration, evaluation, and assimilation. using the data from the satellites to drive the models, and then testing back whether we're actually seeing what we're expecting on the ground. And this is something that the community has been working towards and doing, but it's an interface right now with the research community. And one of the challenges that we have is making that bridge between the regulatory community and the research community. You've heard reference a number of times to NASA's ACAST, the Air Quality Applied Science Team. And this is a really excellent example where NASA invested money in having a set of researchers address problems and issues of interest to the regulatory community. And they did so in order to get NASA data and NASA models being used. But it's provided this great service and this great link. Unfortunately, it's a project. It's a project that was funded for 5 years. It's got 1 more year left, and it will end. And so the challenge that we have is we're building these capabilities. How do we build the institutional linkages and long-standing a sustainable operation here in order to do this? And so that you can have the sophistication that, like Patrick's demonstrated in Colorado and things in a lot of the states where they're facing these challenges. On the international side, the challenge there is to motivate and enable. And it's just worth noting that in some cases in the developing world, satellites and global air quality models and the information that we have may be the best thing that those folks have, because they don't have a robust ground-based network, and they don't have regional air quality modeling capability. Although that's changing rapidly all around the world. But it presents an opportunity for the US and Europe, who do have that capability, to share that information and work with folks. And lastly, there's lots of opportunities to engage internationally, and a lot is actually going on. And I've listed a whole bunch of examples here that I can't go through, but there are opportunities, and the US is engaging, the US government is engaging in work to create public awareness and data availability, to build technical capacity around the world, particularly in China, to work with industry and on sector-specific issues. And methane is a really good example, where picking off the different industrial sectors that have methane emissions, going out, working with that industry, and trying to figure out, okay, globally, how do we get emission reductions? How do we incentivize those? Engaging multiple levels of governance. Sometimes it makes sense to work with national governments. Other times, and you've seen this in the climate world as well, it's like, well, let's go to the cities. Let's go to the people who want to work with us and move the issue forward. And finally, in research cooperation. One of the interesting things about, I think there aren't that many satellites that aren't actually a product of international cooperation. Many of the satellite programs have instruments that have been developed by another country, flying on, in combination with another and stuff. And so there's actually a lot to be dealt with there. And finally, I'll end with, because it hasn't come up yet, and I'm glad I put this in at the end just so I had it, in case it didn't come up, is you just heard from Patrick about tempo, and Brian mentioned tempo before. But one of the really cool things about tempo and what might be coming in the future is that right now, the satellites that we have in space that are looking at air quality are polar orbiting. So they're flying around and they're passing over maybe like once a day and getting a snapshot, okay? So in the future, there are a series of missions that are being planned by the US. The TEMPO project is what is the instrument package that's moving forward. In Europe, there's a satellite called Sentinel-4, and in Korea, there's the GEMS program, all of which will be geostationary. So that means that satellite that's put up staring down and watching the same location all the time. And so you're getting sort of almost constant information and much higher temporal resolution than you'd be able to get with just the polar orbiting. And there's this potential. It's not really clear if it's really going to happen, but if everything comes together right, we'll have these 3 instruments in the air at the same time and be able to see. And there are 3 similar instruments, and so that you'll actually be able to compare information over North America, over Europe, over East Asia. And that's a pretty exciting opportunity. So I'll stop there.